Okay, so the app just told me that you can hear me. I hope this is the case. If someone could a thumbs up or anything in the chat that we know that this is working. I see thumbs up. Awesome. Very good. So 10:01, I will start doing a slow introduction to give also others the chance to join the webinar as well. So first of all, good morning from a heartbroken German. We lost the World Cup yesterday. We're out. Happens. That's not the reason why we're here today. So I'm still quite happy that a lot of you take the time and join our webinar, which is quite. It is about cooling, but nevertheless, it is quite a hot topic these times in data centers. A few words to myself. I'm Klaus Dafinger. I'm based in Germany. I am in the marketing team for Legro Data Center Solutions for Europe. I take care of power distribution, PDUs, the cooling subject in data center, as well as topics all around AI, HPC, and OCP. And this is exactly the reason why we've made this webinar. Because we see a lot of our customers globally struggling with the same questions, the same challenges they see in the data center, which I called is the cooling dilemma. In the times we are in, it is incredible how quickly it is, how quickly things evolving in the data centers. So a lot of customers seeking out and looking for, so what is it that we have to do on a cooling side of a data center to be ready to cool our equipment now, but more importantly and more interesting for them, what is it that we need to put in place so that we are safe for what is coming in 1 year, 2 year, 3 years. So that's predominantly what the customers are struggling with and seeking out what is the right solution. So that's why we're here to hopefully give you an idea of it and also to share with what the trend is and what the customers are choosing to be ready for the future of the data center and to deal with the cooling challenges that they have. In order to do so, there is always something, what is the reason for it, of the cooling challenge, so where it is from. I mean, AI is, everyone uses AI if you want to or not, if it is private, if it is for company, and all of those, and AI development, deployment, and also the training models. This has shifted the density in racks, in servers, especially on a chip base, massively. There was always an increase in power in the cabinets, so that was not a big secret. How quickly things are, I want to say, escalating now in terms of density, that is something that is new. So if you look just a couple of years back, I'm sorry, if you look just a couple of years back, 3 years, 5 years, maybe 10 years, the average density in a cabinet was like 3 kilowatt, 5 kilowatt, then it evolved maybe towards 7 or 10 kilowatt. So there was always an increase in demand and rack densities, depending on the customer base, obviously more or less. The time that we are now in, we're not talking about an increase from 5 kilowatt to 7. We have every couple of months, the big ones, the chip designers, the chip manufacturers, presenting a new technology which can be deployed and which is driving the rack density in an insane speed. So if we look at the chips, what was CPUs is replaced by GPUs, and those things are hungry in power, and they have the density, and they drive the speed and the increase of rack density really insane. So I said, we're not talking about 5 to 7.5 kilowatt or whatever. We're talking about jumps, 50 kilowatt, 100 kilowatt. If you look at the roadmap of, for example, NVIDIA, which I'm pretty sure is a company that everyone is aware of, and the latest designs, which will hit the market in 2 or 3 years, we talk about rack densities from several hundred kilowatts. In the test labs, they're running already 1 megawatt cabinets. This is for sure nothing that everyone will have on a wide scope in the data center. For sure not. Nevertheless, the AI deployment and the impact that we see based on the research of this structure will hit every server and every data center on a different scale. So you will for sure not deploy a 1 megawatt cabinet in the next coming years, but definitely the next cabinets that you will see, that you will deploy, will also have a higher density, probably something around 35, 50, maybe up to 100 kilowatt, plus also new cooling solutions needed based on the architecture of those servers, which we will see a little bit later. So back to that, where is it from? The chips, the development, the density increase of those. So the GPUs, we have different ones. We have the learning models, so where the AI learns if it's a cat or if it's a dog. And then we have the users, which ask then, give me the nice cat images, and then the AI gives you the cat images. So this is one thing where this is driven from. On top of that, we have a second challenge which comes ahead. If we look before that, when typical data center were designed, so they were designed for the overall load of the data center, meaning the total power consumption of the data center, as well as the needed cooling for the full room, for the full data hall. And this changed also, so it's now no longer only the room we're looking at, it is the cabinet we're looking at. So the density shift, the increase is not only on the overall room. The challenge that we are seeing and that our customers are experiencing is the density increase per cabinet. So more higher density on a smaller footprint. So this is an example of a data hall which was 9 megawatt, and it increased on the same space and the same cabinets up to 46.4 megawatt in total, and expanding even further. So it's not before, when an increase was, you place more cabinets and you expand in space or whatever. No, this is the power challenge. Part of this is that we increase the density per foot in an insane amount. So those two, the power distribution to the cabinets, is one of the challenges. This is not our topic for today, but the cooling part. So everything, every kW that you put in electrical energy gets hot at one point, and this needs to be cooled. And this is exactly what our customers are there. So what is it now that I should do, that I have to do? So we have plenty of solutions available. We have the crack and crawl units, in-row as cooling solution. There are rear heat exchangers. Then we have direct-to-chip, so liquid cooling, the servers. We have fan wall and cool walls as option, and also immersion cooling. So what is the way to go? And if just this wasn't challenging enough to choose the right one and to be ready for what's coming in the future, we obviously have a lot more challenges on top of that. So first of all, which I talked about, is the increasing power density on the small spot. Then also the energy efficiency pressure. So those are targets to meet, how efficient your data center runs, because no one wants to waste energy. No one wants to pay for expensive energy if it's not needed. So the cooling solution does not only need to deliver power, it needs to deliver it on a very efficient scale with low running cost, or low as possible, also on low impact on the environment. This could be driven by law, so it could be forced. In Germany, for example, every new build data center needs to hit a PUE of 1.2. It could be also from your enterprise a decision, CSR targets, environmental impact. So all those constraints comes within. Space and design constraints. So this is what I said, that it's now not longer the room that we have to look at. It's really on the cabinet we need to look at. And because of the increase on the small spot, there are risks of thermal hotspots. And then as well, the new cooling technologies evolution, which hit in also to see and to help solving the cooling issues. And for me, just to know what it is, and also to have it a little bit interactive for you, we have a poll that to give me an idea of if you also see any of those as a challenge for you, or what is it that you are thinking about, what you are standing in front of. So I will just give it a minute to see where we're landing and what is it that is interesting to see. Okay, I see. There is a race going on. Yeah. Yeah, we have, I'll give it a couple of seconds more. Still a race, but one is absolutely leading. Okay, awesome. So the poll is over. So the winner, if we want to name it a winner in terms of concerns, is energy efficiency and reducing the POE. So saving cost and also be better and saving the environment. So that was the winner. The second one was supporting higher density loads, followed by future AI deployments, which is very interesting to see. And thanks for that. We know where we are, and this is absolutely something that we will have a look at. Coming back to my slide, the data center cooling dilemma. So crack CROI units, in-row cooling, drilling heat exchanger. So what we will look at in this presentation is we will have a brief overview of those cooling solutions, just in case you're not familiar with them. And then also looking into what are the limits of those potential limits, potential risks, and what is it to be aware of and to do better. And finally, also, what is it that our customers are doing to be ready for what it is. So what is the strategy that is the most advanced to be ready for it? So the first we're looking at is the crack and crawl cooling, which I'm very sure that a lot of you have seen. So if you have a data center, you are very familiar with that kind of solution. So those are the cooling units that stand on the side of the room or on two sides of the room, depending on the design, one or several of those. Well, one, not really, mainly two or several of two for redundancy reasons. The hot air is they blow the cold air into the data center, normally in a hot air or a cold ale, depending on the layout of the data center. The hot air is sucked into them. There is a heat exchanger in them. The liquid, normally it is water, transported outside. It is being recooled by the chiller, brought back in as cold, and then the exchange to cool down the hot air and provide the cold air back to the room, the facility, to the containment. those have been very, very popular cooling solution. Like it was a couple of years back, the standard in a data center. The densities depending on the amount and obviously the capacity of those units. As said, normally they are used in a combination with an hot or cold air containment. So this is one of the key things that you have to be aware of. So with this type of solution or those type of solution, with any classic air cooling solution, airflow management is absolutely key based on the row and or the cabinet level. So what you absolutely want to avoid is a mix of the cold and the warm air, because this runs your efficiency totally south. Another thing is that this type of solution is a central cooling solution which provides the cooling for a bunch of cabinets, a cluster, a cold ale, or whatever. So it is a cooling solution central for several racks. Traditionally, this is brought via a raised floor. The cold air is distributed in the front of the cabinets, and then the servers suck in the cold air to cool them down. The hot air goes out in the back. What you should be aware of is where you place your cabinets. So those solutions work fine if you have a more or less even distribution in density. If you have cabinets with different densities, you should avoid to build clusters within your solution. So you should distribute cabinets with higher loads evenly as possible in your cold or hot air containment, just to avoid the risk of hotspots, which is very important for this. Also, not over exceeding the capacity of the crack and crawl unit. I mean, that should be a thing itself. Airflow management is absolute key for those solutions to make them a bit more efficient. Future expansions and cooling strategies. So this is something that needs to be planned up front, but then again, also strongly limited. So the density, the typical density that you can achieve for those is 15 kilowatt, 20 kilowatt, depending on the solution per cabinet, or on some cabinets, not on all of them. And I said you should be careful with the placement of those cabinets just to avoid hotspots, meaning distribute higher densities of cabinets as even as possible within those solutions, just to avoid them consuming all the cold air provided, and there is nothing left for your other servers. The second solution, I think it's also pretty straightforward, or a lot of you might be familiar with that, which is an in-row cooling solutions. So it is still a cooling solution which provides cold air for a couple of cabinets. The cooling solution moves a bit closer towards the cabinet. So the in-row cooling solution, as the name says, is between the cabinets in your rack rows. The circle itself, as you can see in the image, is quite the same. So the cold air is distributed in front of the cabinets, consumed by the servers. The hot air is sucked in by those again. In the in-row cooler, there is a heat exchanger, which cools down the air and transport it by liquid. There are two types of those solutions available. So it could be a chilled water solution, so based on water, where you have your chiller, or it is a DX solution, meaning direct expansion with gas. This is something that we see more and more as questionable from our customers. So more and more customers choose, if they go for a solution like this, for the chilled water solution and less for the direct expansion, just for CSR targets and for regulations, and also from by law the restrictions and the usage of this gas. So more and more customers avoiding DX solutions as good as possible, just to be on the safe side, because you never know what the regulation in 2 or 3 years might look like on those. There is a downside of these cooling solutions. So the capacity is limited, first of all, on the unit itself, or better to say, on the quantity of units that you can place. Balancing is also something that should be done, just as it is for every solution that provides cold air to a couple of cabinets. So if the cooling solution provides cooling for a bunch of cabinets, then load balancing is always something that you should look into as good as possible, just to have them run more efficiently. Why, we will hear in a minute. Energy efficiency and redundancy. So this again depends on the load. What is also tricky with this type of solution is future expansion. So if your cooling runs on capacity limit and you have to integrate more equipment or more cabinets, the only way you can deal with a higher density is you place new in-row units, which is you lose space in your data center, which is normally absolutely reserved for your cabinets and for your compute power, because this is where you make your money with, or you run your company with, your systems with. So this is not something that is easily given away. And secondly, if you need to install more equipment, so you need to have you're forced to run on a higher density because the systems change in 1 year, in 2 years, in 3 years. It is very, very hard to expand with this solution, because if cabinets are running, they're totally installed, it is very, very hard to move them aside and make space for a new in-row unit. So that's why expansion, everything. So it is a good cooling solution. Expanding with this solution can be very, very, very tricky. And again, you lose space on your white space. So that is something that, depending on the size and the use of a data center, that some customers are not very happy with. Third one, a next solution we're looking at is a cool wall or a fan wall. Depending on the region where you are, you might have heard one or the other name of those. So this is basically one wall inside, or 2 walls inside the data center are replaced with a massive heat exchanger and fans on this. So this provides cold air to the full room, to the full data center, normally in combination with a hot air containment, which redirects the hot air back to the heat exchanger, and then cooled down and brought into the room again. This solution can run on a very efficient scenario. The only thing that is running there to provide a good amount of cooling are the fans. So they need a little bit. They need electrical energy, obviously, to run, but this can run on a very, very efficient manner. The best scenario for this is, again, if the load in the cabinets is more or less evenly distributed. Again, with the placement of those cabinets, you see it visualized red, yellow, and blue. So red are the highest density, so those should be as close, on the closer side towards where the cold air is coming from, just to have the maximum of your cooling. So cabinet placement plays a role in this solution as well. And again, the best efficiency running and the best cooling you can have with this type of solution is the more your cabinets are equally loaded, the better this type of solution will run. Why? And this is something that is shared by all cooling solutions that are cooling a full room or several cabinets at once. Imagine you have a data center where you have 100 cabinets, and then your IT department, your colleagues, or yourself, you see that you need new systems, you need to integrate new systems, you need to deploy AI for whatever reason. So you have new systems in your data center. So the density in some of those cabinets increase. Let's take an example. The average density of your racks was 10 kilowatts on all of those 100, and then you are forced to expand in 10 of those from 10 kilowatt to 25 kilowatt to 30 kilowatt. In order to cool those down, the cool wall, the crack unit, the in-row unit needs to ramp up and provides the cooling power for those 10 cabinets with 25 kW load. To compensate for that, they need to ramp up, and this might end up in a total overkill in terms of cooling power for the 90 remaining cabinet, which just wouldn't need the increase in the density, but in order to compensate for those who have a higher density, that needs to ramp up. So this is something that is shared by cooling solutions that cool either a full room or several of those cabinets. You need to compensate for the most demanding, and it might end in a total overkill for the others. So I'm not saying that you can't cool a higher capacity with those solutions, which is possible on some of those cabinets, but as said, it might end up in it is not efficient at all anymore, because the cooling solutions just need to compensate for a couple of cabinets in order to cool those down, and it might be an overkill. The other points, the load balancing and everything, is something that we already tackled. Again, for this type of solution is also airflow management is an absolute key. As well as, and this is true for every cooling solution, as well as monitoring. So you want to monitor your equipment, your temperature in the front, in the back of the cabinets as good as possible, just to anticipate and see if you run eventually into thermal hotspots and to do something against it. The times that you call your colleague from the facility management and say, our server gets a little bit warm, please change the floor plates with the floor plates with the holes in it, just to have more air in front of the server. So those times are over. So managing your temperatures and running it on a monitoring system is absolute key in the times we are now in for all cooling solutions. We had now a look at the crack, the in-row, and the fan wall, so which are central cooling units, which cooling down either a room or a couple of cabinets. The next one is an air-assisted liquid cooling. So if we look down to the solution itself, it is still air cooling. On the system itself, the change is that we move a lot closer to where the heat is from. So a rear heat exchanger goes on the back of the cabinet. The only hot air we see with this system, or you will have with this system, is basically the distance from the back of your server towards the heat exchanger coil of the rear heat exchanger. So the hot air never leaves the cabinet. What is the benefit of this? Those things can run very, very efficient. They can cool down a huge span of density. So normally they are deployed with loads of 10, 12 kilowatt upwards. Depending on the size of the cabinet and also the rear heat exchanger you're using, they can go up to 150 kilowatt per cabinet. depending on the solution, depending also a little bit on what is the temperature of your facility water and where do you want to run it on. Typically, you not go towards 150 kW because you want to have those run as efficient as possible. So you choose a higher water temperature in, which reduces the maximum capacity of those. But typically, even if you run with 18 degrees, 20, 22, or up to 24 degrees, you can still reach easily up to 100 kW per cabinet with a solution like this. Another benefit is, since we're moving closer to the source of it, and this is attached to the cabinet, we only cool the density of this cabinet. So whatever expansion, whatever you have in the future, if you have an increase in the power of those cabinets, meaning you place more servers tomorrow, in half a year, in 2 years, it is no problem. Everything else within the data center is untouched. So the only ramp up in the cooling power is the demand of this cabinet. So if you have 100 cabinets and 10 of those have an increased demand of cooling density, only those 10 with the rear heat exchanger will deliver the higher amount of cooling, because this is rack level based. So independent of the rest of the cabinet, of the room, each cabinet is handled separately and cooled most efficient. And to give you an idea, so you have water running through those, so you have the electricity, the pumps and everything that needs to run. I'm not talking about the outside plants or not chillers or wherever the water is coming from, because this is true for any cooling solution, so this is equally the same. For the rear heat exchanger, even if those run at 100% capacity, the only thing that you have is they are active, meaning they have fans that supporting the airflow, the hot air out of the cabinet, suck it through the heat exchanger. And even if those, a door designed for 96 kilowatt, for example, runs at 100% capacity, the power draw is 900 watts. So if it runs on 100% capacity. What is also something that is a concern raised very often for this solution, so that's why I'm addressing it, is what if I open the door? Then my cooling for my servers is gone and they will all melt and disaster and everything. No, absolutely not true. In a system, or how the doors work. So with those doors, the data center operator sets the temperature that he wants to maintain in the room. Meaning, if he wants to run his equipment at 24 degrees room temperature, 26 degrees, whatever it is, this is the point that you set within those rear doors, and the rear door adjusts automatically to maintain this room temperature. So that's why it is also in times of expansion, you put more equipment in there, you don't need to worry, because it is adjusted by the rear door itself. So you don't need to open valves, you don't need to change anything in your system. The door adjusts itself by either adjusting the flow rate of the water, so more water through, or adjusting the fan speed. And because of this, if you open the door, the room temperature, since this cabinet blows the hot air in the room, would increase. The other doors around it noticing it, compensated, so they ramp up for the time in terms of service, for so either servicing the door, or because you need to work on it, install new equipment, patch, whatever it is. So they compensate, they run for the time being at a higher pace, so that the room temperature is still the same and is kept at the level that you set, or the operational, manager set for the data center. So even if a door is open or whatever, there is no risk in the system failure, because the cold air in the room is maintained. So, and this is what the server needs to be cooled down. So I'm just bringing this up. I'm just saying this because this is a concern that we've heard very, very often. So the capacity of those doors can be very, very high. Each cabinet is handled individually, which is a very good thing, because that means we can also run it efficient, because we cool the actual demand of this single cabinet independent of the load of any other cabinet within the system. The monitoring and everything is also key with those, and normally those are equipped with sensors, air on, air off sensors over the full height of the cabinet, as well as the water inlet and the water return temperatures, to have this all monitored. And as said, the door, they adjust automatically depending on the load. So this is a type of solution. It is still air cooling, but close to the source of the heat, and this allows this type of solution, first of all, to cool an incredible spread of cooling. So starting from 10-12 kilowatt up to 150 kilowatt per cabinet, and this on a very, very efficient base. If we take a step further and we look at the next cooling solution, so if we remember, we had several of those. We talked about 4. Another solution is liquid cooling, which is a direct-to-chip cooling solution. So meaning the servers getting equipped with cold plates, and the liquid is running through the servers to cool them down. Even if you don't, if you're not using those systems, maybe either you or your kids will definitely have seen them, because a lot of gaming PCs have liquid cooled graphic cards. Same thing, different scale, same principle. So this is roughly what they're using there as well. So there is a hidden challenge with that, and that is not every component in a server is cooled by the liquid cooling by the cold plates. They are normally attached to the CPUs and the GPUs, and what is not cooled are power supplies, memory, RAM, networking, storage, other power distributing components. Depending on the server, there is still 10 up to 40% of the rack or of this system which needs to have air cooling as well. So even with liquid cooling, you need to have a second source of cooling to deal with the remaining heat. Also, not to forget, if you face systems like this, if you deploy systems like this, it is very, very rarely the case that you will go to work on Monday and say, okay, tomorrow we're going to scratch all of our cabinets, we go 100% liquid cooling. It will just not happen. So no one has that. I don't want to say no one, but majority normal companies, normal people don't have the money or not willing to do so. And it's also just impossible to scratch all of your systems and go 100%. So you have also always the challenge of, yeah, I have systems now that are 100% air cooling, and then I need to integrate those for future expansion. So there is always a natural transition of systems. So this is also something that you need the air cooling. So first of all, even those systems need air cooling, and secondly, during the transition phase of I have air cooling and I transition towards liquid cooling, you also need air cooling for legacy equipment. So this type of solution is most of the time used when the cabinets are reaching a density of 40, 50, 60 kW. Then customers start transitioning to those systems with liquid cooling, and then still 10 to 40% needs to be liquid cooled. To have a little bit of easier numbers for that, if we say the total load of a cabinet is 100 kW, and that means that still 10 or 40 kW of those cabinets needs to be air cooled. So that brings us back to our cooling solutions that we have. So you can use the on-chip cooling with a crack and cry unit depending on the systems and the density run. If it is more on the 40 kW side, which is not cooled, then a crack and crawl unit will just simply not be able to provide it the same as a cool wall, just because of the limits of the density that they can handle. Secondly, it's not only that it might work for the moment with the combination of a fan wall of a crack and crawl, so during the transition phase, but that's not the end of the road. So we don't want to plan or build data centers just for 3 years or for 4 years or 5 years. You also want to be ready of what is coming in the future. So what you want to have is as the biggest spread possible, to handle also equipments coming further down the road. So again, one of the cooling solutions, and direct-to-chip cooling in combination with rear heat exchanger. So summary of the on-chip cooling: D2C, DLC, direct liquid cooling, direct-to-chip cooling, different names, same thing. So be aware that it is the CPUs, GPUs, the chipsets that are equipped with those cold plates. So for those systems, you need to have a second source of cooling. What cooling solution you can choose, or what you can use as your second source of cooling, depends obviously on the density of your cabinets. So if it is on a D2C and a crack and crawl unit, D2C and in row, a fan wall, or a rear heat exchanger. This is for now and also for during the transition phase. I highly recommend to not stop looking at the now, also to anticipate what it is in the future, so what it might look in 3, in 5 years from now. As said, we don't want to plan or build data centers for the moment and for now. To keep in mind this one, and we will provide the slides to all of you. There is another cooling solution which we haven't touched yet. I kept this as the last we're looking in, not because it is a bad solution, because it is a kind of a special solution. So immersion cooling, I think some of you might have seen it, might have heard of it. So this is a very disruptive technology if we think about the layout of data centers. So most of those solutions replacing cabinets with a tank. So you can say, without disrespecting the technology, a bathtub where your systems are fully submerged in an oil. So this could be either a mineral oil or a synthetic oil. So your full system is submerged in the liquid and is cooled down with this. This immersion cooling can handle crazy loads, so far beyond 200 kilowatt per cabinet, 400 or even more, depending on the size and the technology. So there are one phase and two phase. A one phase is the liquid is being pumped around those, cooled down, so there is a circle of the liquid in your system. The liquid itself is cooled down. The second one is a two-phase, so the liquid evaporates. By this, taking out the heat energy, goes back to liquid and is brought back to the tank again. Why I kept this as kind of a special? So first of all, it is a totally different cooling solutions. Secondly, even immersion cooling is not the end of the game. Depending on the final technology, on the chipsets you have, if the chip is has a very high density, 1 kilowatt, 1.2, 1.5 kilowatt or whatever, there is still hotspot risk remaining. So even in deployments where customers have chosen to go for immersion, even then they are sometimes forced to have a combination of immersion and direct-to-chip cooling, just because the density on the very small spot, even immersion can't keep up with this density. So even then you have a second type. On top of it, this is also from a day-to-day business point of view the most disruptive technology. So submerging the servers fully in liquid, so you need to have specialized staff, so they need to be specialized trained on this. The liquid, depending on the solution, can reach 35 degrees, 45, up to 50 degrees, depending on the oil, the solution, and also the density of your cabinet. So handling this, they need to be specially trained. Depending on the liquid used, it might need to be tested every year, every 2 years, if it still has the full capacity of redistributing the heat. Sometimes it needs to be replaced, and also for expansions, if your tank, your immersion cabinet is half full, so meaning liquid is full, but only half of it is distributed with servers. If you replace the volume, meaning you put more servers in, you need to take the liquid out, and your staff needs to be able to handle this and do this while it is live. So those type of systems is predominantly used in very, very static systems. So where there is no maintenance needed, nothing, no one needs to touch the system, where is not a lot of movement. And I kind of the feedback from customers, from operators that are maintaining those systems, there is always like the sticky floor around those, because the oil just goes somewhere. So I kept it as last, not because a bad solution, not at all, just a very disruptive technology, changing absolutely the way we are used to having, we're used to cool data centers. As a short overview of our systems, so crack crawling, just everything depends a little bit on the systems and how you use it. For immersion, for example, in the environmental impact, so there are 4 stars that are just half. It absolutely depends on what oil you're using, if it's a mineral oil, if it's a synthetic oil. So that has obviously a totally different impact on the environment and what you can do. Also the complexity of installation and maintenance. So this is for depending on the solution, on the quantity, or if it is really complex to use. Obviously, a central system, which is just one unit that needs to be maintained and be serviced once a year, obviously is less work than if you have plenty of those. For direct-to-chip cooling, it is also a bit more complex, the service and maintenance, just because if an air system fails or is maintained, then there is always a redundancy. And redundancy is either a second unit, a third unit, or whatever, or it is, as an example, in terms of real heat exchanger, it is the capacity that builds your redundancy. So if one unit is in service, the other one compensate with the density for this. For direct-to-chip cooling, that's a little bit different. So if there is a failure, if there is something and the liquid stops running through the chips, that's it. There is no second source of cooling. They may be kept alive for a very short amount of time, because the air or the cold plate can still suck up some of the heat. But if the liquid is stopping to flow, that is very, very quickly the dead end for those chipsets. So this is why it's also complex in installation, just because it is the staff and the installer needs to be trained and also specialized for those type of cooling solutions, just to not have any, for example, simple things like water bubbles in the system. Just because even the smallest water bubble, if it runs through the very, very thin layers in the cold plates, might become an absolute problem. For this, and before I will show you what is the strategic winner, what is I would say minimum 90% of our customers are going for to be ready. We have another poll just to have an idea of what you would see is a strategic cooling solution for data centers. So what is something that you might want to go with? So if we could bring up the second poll. I don't see it now, Dirk. There we are. So just as an overview, so what is it that you see as a potential future of cooling, just to have an idea? Yeah, interesting. There is a clear winner, which is not a big secret, and then we have a closer race. Still some seconds in, I don't think it will change the result of this that much. Very interesting to see, and absolutely this is something that is reflected by the market. So direct to chip cooling as the will dominate in AI deployments over the next 5 years, which is absolutely true. Followed by reader heat exchangers, in-row and traditional air cooling are towards the last place. Immersion cooling is also on place number 3, which is interesting to see. And absolutely, yes, there are systems where structures where we might see them. So thanks for this, very interesting to see. Back to the presentation. So as it was also voted by you, this is what the market is, where the customers are going to deal with what they have now, to have it free in terms of the transition towards liquid cooling. Because if you like it or not, at one point in your data center, you will face servers with liquid cooling, with direct to chip cooling, if you want or not. So you will see those, and to be ready for this, the customers are going, almost all of them, if they go for future builds for new data centers, they go for a reader heat exchanger, because this allows them to bridge the gap from what they have now and the transition towards future deployments with direct to chip. Because if there is a reader heat exchanger, the good news is the liquid is already at the cabinet. So if in the future there is the transition towards direct to chip, there is a CDU which can be placed in the cabinet and then looped in, and the direct to chip can be used. It is also a very sustainable solution to do this, because it is cooling on rack level, so not a room level, which makes it very efficient, because it is just the actual density of the cabinet is cooled down. And with this combination of direct to chip cooling and the rear heat exchanger, you are able to cool down a huge spread in terms of density. And we are almost at the end of the webinar. very happy also to be able to share with you one of the customers that we actually supported and worked together on this type of solution. They did exactly this transition. So they had to redesign, or they redesigned their new data center. So the challenges was consolidate multiple legacy machine rooms into one centralized facility. So they had standard enterprise research computing and high performance computing all together in one. So cabinets mixed with very different loads. The guidelines that they want to have, or what they had, is they had a combination of hot air containment and a crack unit traditionally, and they've chosen to go for the HPC with a reader heat exchanger, which is, if you think of a rack level deployment, also a very nice thing to do, is create different zones. So you have your standard environment, and then if you really have the density, you go with a reader heat exchanger. You can combine this with any cooling solution other than you have. Also for rebuilds or redesigns of your data center, and reader heat exchanger is also something that you can install. Obviously, you need to run the pipes. So there is a little bit of infrastructure work to do, but that's how you can handle them, and that's how they handled it. So they have created zones, crack and crawl units, as well as reader heat exchangers for where it is. The target POE was 1.2, and they expected carbon reduction with all of those and the way. So this was the decision made, I think 12 or 13 years ago, actually. So the step one was with the deployment, there was 5 years in. So after deploying the reader heat exchangers for the HPC cabinets, so they were able to increase the supply water from 18 to 21 degrees. So which is very good, because if you can run on a high water temperature, you can use more free cooling. So the less energy you need to invest to cool your equipment down. And the benefit was also, so the efficiency improvements was, the better the load was varying on the reader heat exchanger, the more efficient the system got, and the better PoE they achieved. So this was step one. 5 years in, they installed the reader heat exchangers, they brought up the equipment, they stacked it in, and everything. So this was the first impact, an overall improvement, PoE achievement, and very smooth running data center, even with the option of increasing the water. The second phase, this was the transition then from traditional air cooling, or from air cooling to liquid cooling. So exactly the transition that a lot of data centers are going through. They have already done this, so they prepared their system, their infrastructure to do this step in the future, because they had seen this coming. So this is the step two. In 2020, there was a pilot project of the direct liquid cooling, which was a test facility for them, how it works. So the in-rack CDUs have been placed. This was looped in with the reader heat exchanger, and then the CDU distributes the liquid towards the reader heat exchanger and as well to the manifold, which then connects via the flexible hoses to the servers, so that everything runs within the cabinet. So the impact on the infrastructure, on the overall infrastructure and data center, was very, very low, because as I said earlier, so if you use a system like a reader heat exchanger, the liquid is already there. So it was placing the in-rack CDU, distributing the liquid, and because of that test in 2023, they started the supercomputer deployment, which have been 16 high-density DL direct-to-chip cabinets. So those cabinets run on 80 kilowatt per cabinet, 60 kilowatt of which is taken by the direct-to-chip cooling, and the remaining 20 kilowatt is dealt with the reader heat exchanger. So they just run at a lower at a lower energy just to deal with what it is, and then they're able to still expand for the future. And this is also a plan that they see. So they anticipate and they foresee an increase of the cabinets or of the load of the reader heat exchanger again from 30 kW to 44 kW, and the full expansion of the data hall. The beautiful news is this was 10 years later, and they have chosen a cooling solution which they made for 10 years. And in all of those time, they never have been forced to change the cooling system. They had to change some pumps for the water flow, but the cooling system itself never needed to be changed. And all of this transition with a span of 10 years from traditional air cooling up towards the way with the combination of direct-to-chip cooling with this type of solution, they have been able to do this and keep the same system for this. And this is what we are very, very happy about, that we could support our customer. And this is just one of our customers. We have several of those stories where we've gone with our customer through that to support them on the transition. This is my final slide, just to give you an overview or a rough idea to what you should look at in terms of deployment, and what is approximately the range that you can deal with crack and crawl units, fan wall units. So this is always bear in mind with the combination of direct to chip. So they can direct to chip, because as said, for direct to chip cooling you need a second source of cooling, and this is the view on the transition in the future. You will see direct to chip cooling systems in your future data center, absolutely. And this is the way for you to map it out. What is it, the density wise, that you can look at to run your systems? And there is the one combination which really is outstanding in terms of the spread. So meaning from the point you can start using it to where it can take you is absolutely the combination of a direct to chip and a rear heat exchanger, and is also compared to the other ones unmatched in terms of not only performance but also efficiency. Having that said, I have one last poll for me, just to have an idea or to get an idea of what is the density that you are running or that you are having right now at the moment. So just to have this on a final idea. Yeah, absolutely. So we're looking at, most of them are in the range of 10, 20 to 50 kilowatts. We also have quite a lot, 50 to 100. And some customers, some of you even run cabinets on above 100. So most of them in the range of 10, 20 to 50. Very interesting to see. But if we would have made the same poll 5 or 6 years ago, it would have looked totally different. And then we would have probably ended at, I don't know, 15 to 20, 25 kW. And if we would do the poll in half a year from now or in a year from now, it will look totally different. Again, we are a little bit over time. I am sorry for that, and not sorry at the same time. I'm very happy that you stayed with me for this. I want to thank you for joining the webinar. I hope it was interesting for you. The questions that have been dropped in the chat, since I took a couple of minutes more of you than I should have. We will get back to you with the questions, and we will provide the answers to all of you via email, the same as you will have access to the slides of this webinar. Again, thanks for all of you. And having this said, I want to inform you that next week we have another webinar if it is interest for you. It is strategies for modern data centers. So is your data center truly secure? Which has a view on cybersecurity in terms of not your equipment, not your firewall or whatever, cybersecurity, and how PDU and KVM can support you on this and what they can do for you. Having this said, again, thanks to all of you, and I wish you a very, very good day, and hopefully see you next time.